So I'm Bruce, and today I'm going to be talking about climate-dependent passive house standards. In other words, instead of using one standard for the entire world, this is about specific climates and standards for each climate. And let's see, this is based on research I did over the last couple of years while I was getting my master's degree at CU Boulder. In their building systems program, and it's nice to be able to share this with this room because it was an academic work, and not many people have heard about it yet. So I'm excited to be able to be here and share it with all of you. Let's see. First, I have a question for you. I had a manila folder and a little package of paper on top of it, up on one of these front seats that maybe someone picked up when they put down a laptop on top of it and then picked up the whole deal maybe. So, well, if it shows up, okay, that will be nice. So, so I'm going to focus on the method that I developed. I will share some preliminary results at the end, but mainly I'll be talking about a methodology. And it's a computer-based methodology. It is deterministic. In other words, it will just determine standards for you. That's not to say that I don't think there should be human judgment involved in the final process of figuring out what the standards should be. So this is just kind of a first step in that whole process, hopefully. I'll just go ahead and get started. So here's a quick overview of what I'll talk about. First, I'll talk about why I think climate-dependent standards are needed. Then I'll talk about the method, starting with some general ideas, kind of where I was coming from, what I was trying to accomplish with the method. I'll talk about software tools that I use, BEopt and Energy Plus, and why I use those computer simulation tools instead of PHPP. And then with that background, I'll be able to get into the more details of the method. Then I'll share some results with you, including some potential or preliminary standards that resulted from the method. And one question I had was, as probably all of you have heard, Dr. Feist claims that in Germany, the passive house standard can lead to 90% reductions in heating energy consumption. And I was curious if that kind of achievement was possible here in the United States. And so I have some numbers there. And then finally, I'll wrap up with conclusions. So this question is a source of debate in the passive house community. So I'm just going to try to quickly give you my take on why I think climate-dependent standards are needed. Right now, we have the existing standard that was developed for the Central European and German climate. And if you think about the annual heating demand criterion in Germany, that leads to a certain kind of building type. It's a high-performance building, for sure, but it's also a buildable building, and at least from some point of view, it's an affordable building. It's climate zone 5, if that means something to you. However, if you move your frame of reference and think about being in a much colder climate, it might still be possible to meet that standard, but clearly it becomes less and less affordable as the climate gets tougher and tougher, and therefore, in my opinion, becomes less of a practical standard. If you flip it over and go to a milder climate, like San Francisco or Los Angeles, I think you're leaving some potential energy savings on the table by using that standard. The existing cooling demand criterion has the same problems, but also has the additional problem of, I think, being arbitrary. It looks like they, somewhere along the way, just said, we'll set it equal numerically to the heating demand standard. So just to wrap that up, in tough climates, the existing one standard discourages adoption of the standard, and in milder climates, energy savings are unrealized. So now we'll get into my method, and first I'm going to try to give you just a speak in general terms and give you an idea of what I was shooting for. So I had these two big ideas in mind. The first is what I see as the fundamental passive house design principle, that you're trying to design a building, an envelope of a building that minimizes heating demand and cooling demand. Everything else comes later. The second big idea is that, in my opinion, performance standards have to have these three characteristics. They have to lead to buildings that are more efficient than what's typically being built. They have to lead to buildings that are technically feasible. And the third, and in a way most important thing for my work, is that they have to produce buildings that are affordable. It doesn't mean the cheapest, most inexpensive possible, but it means they have to be affordable in some sense to it. Yes. Well, I wouldn't say I'm throwing out. I agree with that methodology, but I don't think has to be there. I mean, I don't think it has to be the only way of supplying heating and cooling. That's the best way to say it. So to get at that first idea, I wanted to preserve that fundamental passive house design principle, but I needed a single measure of performance. And so I've combined the two and created space conditioning demand. It's simply the sum of the heating demand and the cooling demand. And I believe that passive house standards should be based on that concept. So first of all, I think that preserves the goal of minimizing heating demand and cooling demand, because you're trying to now minimize their sum, so you're still working towards that really efficient building envelope. But I also think it allows the designer more flexibility, because as you probably know, there are trade-offs between heating demand and cooling demand. And rather than having to meet both of two separate standards, you can now meet one and kind of play with things like window area and whatnot that affect both heating demand and cooling demand. The second thing, the idea about being able to measure affordability. To create the standards, I needed to come up with a way to measure affordability instead of just saying, well, it's sort of subjectively we think it's affordable in such and such climate. I needed an objective measure. So a simple way of doing that would have been to use something like simple payback and say it needs to pay for itself in 10 years or what have you. But really, that's kind of a crude approach, and so I've come up with something that's hopefully more sophisticated, and it's certainly more complicated, for better or worse. As you'll see, there's kind of a two-step process. The first step is to calibrate this measure that I'll describe in a few minutes against the passive house standard. The idea there is that I want my method to basically, if it were applied to Germany, I want it to produce the same numeric value that's used now for the standard. So there's a calibration step. And then once that's done, then it can be applied to any other climate. And the idea is to determine the highest level of efficiency possible in that climate that has the same degree of affordability that the current standard has in Germany. All right, so I mentioned that I did not use PHPP for my computer simulations. There are two main reasons for that. One is that I did some extensive investigation into the accuracy of PHPP, comparing it to Energy Plus simulations, which I believe is considered the industry standard, which has been extensively tested. And I found, I found lots of inaccuracies and in different areas. So this could be a whole other talk. I won't go into this too much, but there are problems with climate changes. If you move a building between a moist climate and a dry climate, there are problems with modeling slab installations, problems with modeling the large amount of solar gain that we had in the U.S., and some other things. And not surprisingly, there's greater inaccuracy in predicting cooling demand than there is in predicting heating demand. The second reason down at the bottom for not using PHPP is that I needed to be able to do optimizations, and that's not part of PHPP, and it is part of BEopt, which is the tool that I use. There was a session yesterday, a workshop yesterday about BEopt, so maybe some of you heard about it there. It's a tool that was developed at NREL, the National Renewable Energy Laboratory, not too far from here. It uses Energy Plus as its simulation engine, and one of the most important things that BEopt does is it lets you easily run optimizations on your building design. So you set the footprint and the dimensions of the building, but then you can vary insulation levels and window types and all sorts of things, and it will compare annualized costs for all those different combinations and tell you what are the most efficient choices out of what you've specified. So I'll be showing you some graphs from my results, BEopt graphs from my results. So I wanted to show you a quick sample graph from BEopt. Basically, as I said, you specify a range of combinations of insulation values, window types, all sorts of different building elements. And BEopt will automatically come up with combinations of those and run as many simulations as it needs to sort of survey those different combinations. And on this graph, all those different points, the gray points as well as the darker black points, they all represent individual house designs, individual combinations of those different energy efficiency measures. And typically you get this, well, let me first say that, in case you can't read it, the vertical axis is about annualized costs, which reflect construction costs and ongoing costs for replacement of building elements and energy costs. And the horizontal axis is source energy savings. So basically, as you move to the right, you have a more and more energy efficient building. And you typically get this swoosh curve because the buildings over to the left are the least energy efficient. And at the beginning, as you examine ways to improve the building, there are lots of options, and lots of them are cost effective. But at some point you reach a minimum annual cost, and it gets harder and harder to improve upon that performance, and so the curve goes up to the right. Yes?
Can you just clarify one thing about this idea, which is obviously operational cost is energy field, right?
Yes.
So are you going to say something about how you pick energy cost to start with and how it changes over the life of the building for these simulations?
Yes, I'll answer that to some degree later on, but I can also say now that it doesn't have a terribly sophisticated lifetime energy cost model, so it has the ability to specify fuel escalation rates, and that's about it. All right, so now with this background that I've provided, I can talk about the method in a little more detail. As I've said, part one of the method is calibration. And the idea is there to use BEopt simulations. And in my simulation, I was running about something like 500 different designs for the buildings every time I did an optimization. So I was looking at basically typical construction all the way up through super energy efficient, essentially the best we can possibly do these days. And so part one, the calibration, was in the German climate to look at a BEopt optimization and kind of turn the economic dials until I found conditions that made sense that produced, or I should say, where passive house design coincided with the most energy efficient design that could still be considered cost competitive. So it's a mouthful, right? But it's if you think about it on the graphically, it would be a point on the graph that's pretty close to the minimum point, pretty close to that sweet spot. Maybe a little bit further to the right, but not much further. I wanted passive house design to land right there. And so most energy efficient, I'm defining as having the lowest space condition demand. That's the sum of heating and cooling. And I wound up defining cost competitive as being within $100 per year for the minimum annualized cost. part two of the method is the application to any other climate. So I would take those economic conditions I found in Germany and then apply them anywhere else. And I'd again use that same graphical output, the same BEopt optimization kind of work, kind of approach. And this time look for the most energy efficient building within that range of buildings of the process. And then that building would provide the basis for a standard. Before showing you results, I want to say that my work was limited to single-family homes, single-family detached homes. It's partly because that's what BEopt was designed to model, and also because I needed to limit the parameters of my investigation for the sake of getting it done at some point. So the base building was meant to represent what's typically being built in the United States. 2,000 square feet, has a slab and a vented attic, but I did apply passive house standard air tightness to it. And then I varied insulation levels in the envelope and varied window types and area and distribution. And to provide a little bit of variability in the shading, I varied the length of the eaves. So here's the graphical output from the first step of the process. And here we have a different, another BEopt curve that's similar to the one we saw, but they all vary a little bit in their shape and whatnot. And so here I used 30-year project lifetime and 0% real fuel escalation rate. And I used German utility rates, which, if anyone is familiar with European fuel rates, they know that they're sort of 2 to 3 times what they are here in the United States. So they're significantly higher. And the point over here that's highlighted on the graph over to the right is the first point, as you move to the right, the first point that meets the passive house standard. And so it's not terribly close to the minimum cost point. It's pretty, there's a fairly large cost premium there. Oh, so well, it's basically meeting the annual heating demand of 4.75 kBTUs per square foot per year. I'm sorry? Based on BEopt's output. And there was some manipulation needed because BEopt doesn't output heating demand, but it's possible to calculate. And that reminds me that in Germany, cooling demand is not really much of an issue. So it's, in this case, it was really about meeting the heating demand, and then the cooling demand just happens automatically. So as I said before, the next part was to kind of turn the dials on the economic conditions and look for a way to make the passive house design close to the minimum cost point. Yes?
Can you say what the base case
The
was?
base case for?
For that last track. Extraordinary savings percent a year over what base?
I'm sorry, I don't understand.
What's the reference case?
Oh, I see. So you're asking about the horizontal axis, source energy savings? Right. So the vertical axis in BEopt is a little confusing, and I don't want to get too into it, but it's relative cost.
It's just a question of what's your base case?
Right. So it's essentially this building with what I considered typical construction, and for that I used Building America benchmarks. I know I was doing modeling in Germany, but I needed some standardized measure of what's typical construction. So it's more or less right. Right.
And the source energy is just for thermal load, heating and cooling. It's not anything else wrapped into it.
In my optimizations, yes, that's true. Yes. Right, but the thing is, I'm not totally interested in that baseline. I'm interested in what happens way to the right. You know, I'm interested in what happens in the realm of high efficiency buildings. So the you know, the numerical, the fact that it's 42% savings, that's not very meaningful. Right. Yes. Right. But this is the BEopt algorithm. So this is the result of adjusting utility rates a little bit, increasing the project lifespan to 50 years, and adding a little bit of fuel escalation rates. And those represent the economic conditions that I would then take and apply to any other climate. And so I have 3 examples here. There are 15 climate zones in the United States. I used a representative city for each of those 15 climate zones. So in this case, we're seeing results from Chicago for climate zone 5A. And again, I took those same economic conditions I had found in Germany and ran the optimization, just changing the climate essentially to Chicago. And in essence, what I did was kind of just find the minimum cost point, move out as far as I could to the right, as long as I was staying within $100 per year. But simply, more graphically, I'm just looking at a small region around that minimum cost point and pulling out the highest performance building out of all the buildings chosen. I wanted to show you a couple other examples just to show the kind of effects that different climates have. So here's Phoenix, which is extremely hot and sunny. And you see that over on the right, so I'm going back to Chicago now. Over on the right, the curve kind of just comes up relatively gradually. In Phoenix, the curve really shoots up almost vertically. And that's because it's really hard to reduce cooling demand past a certain point. Right? Adding super expensive windows, going to R60 walls, just has not that much of an impact on cooling demand the way it does on heating demand. Whereas in Minneapolis, it's a flatter curve. That tail end is flatter. So for each of these 15 climates, I did optimizations like this, pulled that point out of the data, and took the heating demand and cooling demand numbers from that data, combined them into my space conditioning demand number, and then that forms the basis for a preliminary passive house standard. And so these next 2 slides show the preliminary standards I came up with. And I'll talk a little later about why I think they're preliminary. But we have 2 slides because there are 15 different climate zones. So this slide shows the hotter climate zones, the representative city for the climate zone, and then the SCD is space conditioning demand, which is the sum of the next 2 columns. And I show those columns just centered for reference because we're, I think, more used to looking at heating demand and cooling demand numbers. Yes, total. And I included the Hamburg numbers just kind of for reference. So on this slide, there are kind of 2 main results to look at. One is that in the very hot climates of Miami and Phoenix and even Houston and Las Vegas, you see very high numbers. Right? The cooling demand numbers over on the right do not meet the 4.75 standard. They're not even close. And so this method implies that in some locations, the passive house standard should be relaxed, especially on the cooling demand side. The other thing that we can see right away is that this method implies that the standards will vary quite a bit, climate zone to climate zone. You can see San Francisco, the bottom basically, the method is basically saying you don't need heating or cooling in San Francisco, which may be appropriate. Yes.
I just want to say a couple of things. First of all, you haven't said what the heating is, and your optimization graph in terms of source energy, and this is demand. And I think sources is absolutely right when you focus on it. And when you apply primary energy factors, you factor cooling demand is lower than consumption because CO2 and heating is fossil is higher, then we really have to take this one more step and look at the true power energy impact. And that would be where we really start to see the effects of this, because those numbers, they're bigger if there's demand and capital costs. I think London focuses so much on site energy demand, it doesn't focus on primary energy. And so you're getting there, and your graph of all the optimizations of source energy, but this is demand.
So two things. One is that typically cooling is provided through the use of electricity, and the site source factor conveniently roughly cancels out the COP. I know it's not exact, but that's one way of thinking of it. And also, I would argue that you have to worry about the demand values first. And I totally agree that total source energy is extremely important. But in a building, you worry about, I think, you worry about the demand and cooling first, and then you figure out, what does that mean for what kind of standard we should have for primary energy demand. So I did not, in my work, I did not address the primary energy demand criterion. It's not because I don't think it's important. It's just because I think this should come first.
But you optimize this one primary.
Yes, but yes.
Yeah.
Okay, I think I need to move along. But thanks for the question. Yes.
Did you use always the same area of the windows?
No, that was a variable. And of course, the results tended to say that smaller windows are better. So I think, to do this kind of work, you need to say there's a minimum, maybe there's like a minimum acceptable window-to-wall ratio that we should use. So that's essentially what I wound up using. Yes? That's correct. And it's another limitation of the work I did. Like I said earlier, I needed to keep the options finite. And according to Census Bureau data, what that slab on grade is actually the most common foundation being built in the United States. So here's more of the same as just for the colder climates. And now we see it's almost the reverse. So we see numbers that are quite a bit lower than the 4.75 of the existing standard, which means that the method implies that in the colder climates in the United States, except for the extreme of Fairbanks, we should be able to have a tougher standard than what's existing. Most probably that's because of the high levels of solar gain that we see in the United States. We could talk about these numbers and look at the tables in detail for a while probably, but I want to move on and look at what I'm calling reductions versus typical construction. So I mentioned this question early on that I wanted to find out how much, what kind of reductions we could expect from the standards that follow from this method. What kind of reductions would those lead to compared to normal typical construction? And here we are back again in the hotter, warmer part of the country. And over to the right, under cooling demand, you see values from roughly 50 to 70%. So again, that points to the fact that it's just harder to really eliminate the need for cooling demand, as long as you have a set point, a temperature set point of what's considered comfortable. If I move on to the next slide, which is the colder climates, and we look at the HD column, the heating demand column, then we see numbers that are comparable to what I've heard for Germany, the 90% number. So we have 85 up to 95, 97%. But I think most importantly, if we look at I'm going to go back a slide. If we look at the SCD column, the space conditioning demand column, we see in all climates, we see decreases of at least 50%. Miami and Phoenix are extremely difficult climates. And then in the other climates, we see reductions of 70, 80%, and then in the colder climates, up into the 80s and the 90s. So I think the message there is that these standards that would come from this method would produce results similar to the passive house standard as it is applied to Germany. Oh, it's a negative, right? Is that the one you're looking at? It's so the negative reduction is the negative 148% is an increase, and that's because of the trade-offs that the optimization did between increasing or decreasing heating demand and cooling demand. 5 minutes? All right, so I'm going to wrap up, and I have 2 slides of conclusions. First of all, I feel that this is a promising method, and as I tried to say at the beginning, the real work I feel I've done is creating a method. So I wouldn't put too much stock yet on the numbers I've shown in the last few slides. I've really been focusing on the method. The second thing is that doing this work has really made me think that climate-dependent standards should be used. Clearly, they will vary greatly across the United States, and they're going to be quite different from the existing standard. As I've explained, I think they should be based on the space conditioning demand, the sum of the two, heating and cooling. And as I was just saying, I think they can lead to pretty dramatic reductions in space conditioning demand. I just want to end with some ideas for what would be needed next before this could be considered more seriously, and certainly before it could be put into production, as it were. So one big need is to explore other building types, not just single-family homes. Another thing is I was not able to fully explore climate-specific house designs. And the biggest example of that is extensive shading that could be used in the warm climates. If you look at the different preliminary standards for different climate zones or cities, there's a lot of jumps between adjacent climate zones that that would have to be addressed. Because what do you do if you're right near the border of 2 climate zones? It's not clear which one you would want to use. And it's possible that could be addressed by some kind of correlation with heating degree days, cooling degree days, and possibly bring in solar gain values. And then finally, a really thorough review of all the options and costs and specifications I used, especially in the high performance area. That's all I have. And